Hello everyone, I am Vinu Priya, Assistant Professor in the Department of Mathematics, DKM College for Women, Vellore. Today we are going to see about abstract algebra. The topics are basic definition of groups, examples, subgroups, theorems on subgroup. Before entering to the definition of a group, we need to know what is a binary operation. Binary operation is a rule that assigns to every pair of element to any unique element of that set. That is, a mapping asterisk S cross S to S itself is called the binary operation on the set. If I write A asterisk B, here A and B are called the operands and asterisk is called the operator. The usual addition, multiplication, subtraction, division are the examples of binary operator. Now we are going to see the definition of a group. A non-empty set G with respect to a binary operator is said to be a group if it satisfies the four conditions. The first one is closure property, associative, identity and inverse. Now we'll see in detail. A non-empty set G is said to be a group if it satisfies the following condition. The first is closure. For every A, B belongs to G, here the binary operator what we have taken is product. So A product B also belongs to G. Associative means for three elements A, B, C belongs to G, then A product B product C is equal to A product B product C. Then existence of identity element. There exists an identity element E belongs to G such that E product A equal to A product E. Existence of inverse. For every A belongs to G, for every A belongs to G, there exist an elements A inverse belongs to G such that A product A inverse equal to E equal to A inverse E. If all these four conditions are satisfied, then the set is said to be a group. Along with the fourth condition, if it satisfies a commutative condition, that is A product B is equal to B product A, then it is said to be an abelian group. If this condition is not satisfied means, then it is said to be a non-abelian group. So here the first condition is closure, second is associative, third condition is identity, fourth condition is inverse. If these four conditions are satisfied, then it's said to be a group. Suppose a non-empty set satisfies only the first two conditions, closure and associative means, then it is said to be a semi-group. If a non-empty set with a binary operation satisfies the three conditions, closure, associative and identity, then it is said to be a monad. If it satisfies all the four conditions means, then it is said to be a group. In addition, if it satisfies the abelian condition, commutative condition means, then it is said to be an abelian group. Now we'll see an example. So here, first we'll see an example of a semi-group. N. So N, the set of all natural numbers, 1, 2, 3, etc. So here N is a semi-group with respect to addition. Semi-group. This is a semi-group. Okay, because with respect to addition, the additive identity is 0. Natural number starts from 1 onwards. So the identity element does not exist. So N is an example of a semi-group. Now we'll see an example for a monad. Monoid in the sense it must satisfy three conditions: closure, associative and identity. So the whole numbers starts from 0, 1, 2, 3, etc. So here whole number with respect to addition is an example of monoid. Because here the inverse of 1 is -1. That does not exist in whole numbers. So here the set of all whole numbers with respect to addition is an example of monoid. The set of all integers with respect to addition is a group. The set of all 2 cross 2 matrices A, B, C, D, where A, B, C, D are real numbers and AD minus BC is not equal to 0 is a group under multiplication, matrix multiplication. G is equal to the set of all numbers 1, -1, I, minus I is a group under multiplication where I square is equal to 1. Next, the order of a group. The number of elements in the group is said to be an order of a group. The groups may be finite or infinite. If the number of elements is countable, if it is finite means then it is said to be a finite group. If it is not countable means then it is said to be an infinite group. Next definition what we are going to see is subgroup. A non-empty subset H of a G is said to be a subgroup under the operation. Here the binary operation what we have taken as product. If H itself is a group. If H itself satisfies the 4 conditions, that is closure, associative, identity, inverse, then is said to be a subgroup. Next we are going to see a theorem, necessary and sufficient condition for a subset to be a subgroup. First we should know what is necessary and sufficient condition. Necessary condition in the sense the statement should imply the condition, that is the necessary part. Sufficient means the condition should imply the statement. So here the statement is H is a subgroup. So what is the condition? It must satisfy the 2 conditions, okay, equivalent conditions. So to prove it is a subgroup, it's enough if we prove the closure property and inverse exists, okay. Now first necessary part will assume that H is a subset. The necessary part will assume that H is a subgroup of G. Now we have to prove that the closure and inverse exist. See, if H is a subgroup means obviously it will satisfy the 4 conditions: closure, associative, identity and inverse. The first condition is closure, the second is inverse. So the necessary part it is obvious. Now we are going to prove the sufficient part. To prove the sufficient part, we'll assume this closure property and inverse exist. Using these 2 conditions, we are going to prove it is a subgroup. Okay. So here already closure property is there and inverse is there. What is left is we have to prove it is inverse, that is identity element exists and associative condition. These 2 conditions we have to prove. So I am taking an element A belongs to H. Okay. By the second condition, inverse exists. A inverse also belongs to H. Now I am using the first condition. What is the first condition? If AB belongs to H means then the product will belong to H. Now A and A inverse belongs to H. So the product definitely it will belong to H. What is A inverse? That is the identity element E. So identity element exists. So first condition closure is proved and identity element inverses exist. Only associative condition we are going to prove now. So H is a subset of G. The elements of H are the elements of G. The G is a group. The elements in the group will satisfy the associative condition. So the elements of H also will satisfy the associative condition. Since all the conditions are satisfied, now we can tell H is a subgroup. Okay. We'll move on to the next theorem. The necessary and sufficient condition for a non-empty subset H to be a subgroup is if A comma B belongs to H implies A inverse belongs to H. Here the necessary part, the same thing, if H is a subgroup. Using this statement, we are going to prove the condition A, B inverse belongs to H. Okay. So here first what we are going to assume is H is a subgroup. Subgroup in the sense four conditions: closure, associative, identity and inverse. All the four conditions will be satisfied. So here I am taking an element A comma B belongs to H. Okay. Now since H is a subgroup, we are assuming H is a subgroup. If H is a subgroup means definitely the inverse will exist. So B inverse belongs to H. So A belongs to H, B inverse belongs to H. By closure property, A, B inverse also belongs to H. So the necessary part is over. Now we are going to prove the sufficient part. The sufficient part is we are going to assume the condition A, B inverse belongs to H. Using this condition, we are going to prove it is a group. Okay. So first we have to prove closure. Okay. So here let me assume I'll take A comma A belongs to H. See, what is the condition actually? If I take A, B belongs to H means first element remains the same. The inverse of the second element. We are going to take the product of the inverse of the second element. So here I am considering A comma A belongs to H. So this can be written as A dot inverse of the second element belongs to H. So A inverse is nothing but E belongs to H. So the identity element exists. Now I will consider E belongs to H and A belongs to H. Use the same condition. So E inverse of the second element, A inverse. This is the assumed condition. Okay. So identity element into A inverse is A inverse belongs to H. Okay. So here identity element we have proved. Then the existence of inverse we have proved. Now we are going to prove the closure. So for that I am taking A comma B inverse belongs to H. Use the same condition. The product of the first element and inverse of the second element belongs to H. A inverse is nothing but B. So A dot B belongs to H. So here the closure property is satisfied. Existence of identity and inverse is proved. Only the left out is associative. As I told you already, H is a subset of G. The elements of H are the elements of G. G is a subgroup. So obviously H will satisfy the associative condition. So all the four conditions are satisfied. Then we can tell H is a subgroup. So the equivalent condition to prove H is a subgroup, it is enough if we prove that A, B inverse belongs to G. A, B inverse belongs to H. Next theorem, if H and K are the subgroups of G, then H intersection K is also a subgroup of G. So in the previous theorem we have shown that to prove it is a subgroup, it is enough if we prove that A, B inverse belongs to H. Okay. So here they have given as H and K are the subgroups of G. Okay. So the given condition is H and K are the subgroups. H and K are the subgroups. So what we have to prove is H intersection K is a subgroup. Okay. So I'll take two elements, that A comma B belongs to H intersection K. Intersection means A comma B belongs to H and A comma B belongs to K. H and K are subgroup. Subgroup means it will satisfy the condition A, B inverse belongs to K. So A, B inverse belongs to H, A, B inverse belongs to K. So this is common to both H and K. So I can tell A, B inverse belongs to H intersection K. So from here we can conclude that H intersection K is a subgroup. The second theorem is union of two subgroups need not be a subgroup. See, whenever we need to prove the theorem is not true, it's enough if you give an example and show that the condition is not satisfied. Okay. So let me take a subgroup H 0 plus or minus 2 plus or minus 4 etc. This is a subgroup. I'll take another subgroup 0 plus or minus 5, plus or minus 10, etc. Now I'll consider H union K. Union means either it can be in any one of the set. So 0, plus or minus 2, plus or minus 5, etc. Okay. Now I am going to show that it is not a subgroup. To prove, again, you can give any one example. I'll take an element 2, 5 belongs to H union K. So with respect to addition, so 2 plus 5, it is 7. 7 does not belong to any H union K. So the closure property is not satisfied with respect to addition. So the union of two subgroup or union of subgroup need not be a subgroup.